We're going to start on the third unit here, beginning with chapter 6. So you might remember that earlier on I said we would come back after chapter 2 and kind of refine our model of the atom a little bit more. So really we kind of left our atom with that planetary model with electrons circulating around the nucleus, and we want to come back and refine that a little bit. So while we're here, I think I can briefly remind you about that part, right? Essentially, we imagine that we have our nucleus in the center and then concentric orbits around it of some type. And where we're headed now is what we call the planetary model, where the plus charge is concentrated in the nucleus, and then these orbits are containing our negatively charged electrons. So that's the picture that we want to get to, but we want to think about it in a bit more detail. So in this chapter, we're starting to consider the electronic structure. So the location of the electrons, the behavior of the electrons, and how that's going to help us understand essentially how atoms are going to come together to form molecules. So I would say over the next 4 sets of slides, that's where we're headed broadly, is to get to a point where we can understand how atoms form molecules, how we can understand the behavior of those molecules, and the shape of those molecules. So we're going to start our trip towards making that all come together by thinking about the behavior of waves. So let me say kind of 2 things that we're interested in thinking about with regard to waves. The first thing to consider is the way that the electronic structure of atoms was further probed, the way we got a better understanding of what's going on, is by observing how light, electromagnetic radiation, interacts with matter, interacts with atoms and molecules. So that's our primary focus going in, that if the interaction between light and matter helps us understand the true behavior of matter, then we should start by having a good picture of how light is actually behaving when it interacts with matter. So that's the first part, and that's the main part that we're going to focus on early on in this chapter. But later on, we're going to see something else important, and another reason for us to focus on the behavior of waves. Later on, we're going to learn that the behavior of electrons is somewhat wave-like. So it'll turn out a lot of the things we're talking about with regard to the behavior of waves will also apply to the behavior of electrons. Okay, so let's start here and focus first of all just on considering how light behaves as a wave and how that helps us understand the behavior of matter a little bit more. So let's start just by imagining that this is a wave and it's traveling in this direction. So you can imagine it like an ocean wave where there are crests and valleys, and it's traveling in a particular direction. So if we consider a wave, there are 2 parameters that we want to think about initially just in this picture. One is the wavelength, and I think the easiest way to visualize the wavelength is to think about this peak-to-peak distance. And we can measure this in all sorts of units. This is lambda. That's what we use to symbolize wavelength. And it could be in any units, could be in meters or centimeters. We're going to actually see it fairly often in nanometers because that's going to correspond to the wavelengths for visible light. So that's something that we're going to want to be able to think about as we go forward. A parameter that we're not super concerned with right away, but something we should be thinking about if we are talking about a wave, is the amplitude. And the amplitude is basically saying when I cut this wave in half, how far does it extend above that line or below that line? It's going to be symmetric about that line, but the amplitude is really how tall the wave is, if we want to think about it that way. So same thing, I would be measuring this in some sort of length unit. We're not going to spend a whole lot of time thinking about amplitude, but whenever you're thinking about a wave, it's a good parameter to consider. So wavelength we can define as the distance along the direction the wave is traveling for a full cycle of the wave. And what we mean by that is from this point we go down and then back up to the maximum. That's a full wavelength. So the peak to peak distance is what I'm thinking about there. So here we're saying the distance between corresponding points on adjacent waves is the wavelength. So basically saying how far it is from one cycle to, or for one full cycle in the direction that the wave is traveling. Well, generally, what we're going to be interested in is the wavelength and the frequency. And the frequency, it looks like a letter V, but this is the, oops, I didn't do a good job of drawing it myself. This is the Greek letter nu, and that's going to be the way that we measure frequency. So frequency is thinking about if I'm stationary and observing the wave traveling by, how many full cycles of the wave am I going to observe per second? And so when we think about what a cycle would look like, it's a full wavelength essentially. So, oops, let's see, it doesn't look like I can make any useful marks there, so let me try to circle it. So that's one wavelength, right? Peak to peak distance here. Then what we're looking at is 3 different waves, just so we can help visualize what one wavelength is in each case. So if we're talking about light, electromagnetic radiation, then it doesn't matter what it is, whether it's X-rays or visible light or infrared or ultraviolet. If it's electromagnetic radiation, it's all going to be traveling at the same velocity, the speed of light. So light and electromagnetic radiation, those are terms that we should use interchangeably. And the speed of light in SI units, rounded to 3 significant figures, is 3 times 10 to the 8th meters per second. So again, whatever electromagnetic radiation we're talking about, that's the speed at which it's going to travel. So again, imagine that our waves are traveling in this direction, and we're just going to be a stationary observer somewhere watching the waves go by. I don't know, let's say we're here. So if the wave is if all these 3 waves are traveling at the same speed, and I'm stationary watching the wave go by, when we talk about frequency, we're asking how many full cycles of the wave will I observe per second. So if the wavelength is long, again, remembering these are all traveling at the same velocity, then I will see fewer cycles per second, like in case A. But if the wavelength is short, like in case C, then I'll see more cycles per second. And in fact, we can even go further and say that wavelength and frequency are going to be inversely related. So the picture we're supposed to see here is that the wavelength in case A is double the wavelength of case B, and 4 times the wavelength of case C. So as the wavelength decreases, the frequency is going to increase. So when we talk about cycles, we mean a full wavelength worth of the wave. So it should make sense that as wavelength decreases, frequency increases because we're going to see more cycles of the wave per second. So then we would say lambda, the wavelength, is inversely proportional to nu, the frequency, or lambda nu equals constant, right? If one value goes up, the other one goes down. If one value goes down, the other one goes up. Well, what is that constant going to be? It's going to be the speed of light, and we can make sense of that with the units in just a second here, but basically we're multiplying a length unit by how many times something is happening per second. So we're going to get length, whatever it is, divided by seconds. So that'll give us a velocity. Okay, and then here down at the bottom it says the longer the wavelength, the smaller the frequency. So we're being pretty precise with our language there, right? Wavelength is how long it is. Frequency is going to be large or small. So that's going to get us to our equation C equals lambda nu. And that's the first equation that we want to get comfortable with in this section. Let me just kind of show you unit stuff real quick, right? Lambda will be wavelength. And let's say in this equation we want to use it in meters. Nu will be frequency, and some books use an F for this. I'm pretty sure our book uses a nu, and that's going to be in seconds to the -1, which we'll also find out is called hertz. I think we'll bring that up in a couple slides. But so then if you think about it, lambda times nu will be meters times seconds to the -1, or meters per second. So as long as we're using our wavelength in meters and our frequency in seconds to the -1, the units we're going to get out for the product of lambda and nu is meters per second. So because all these waves are traveling at the same velocity, the product of meters and seconds to the -1 is always going to be equal to the velocity or the speed, which is 3 times 10 to the 8th meters per second. So there are a lot of ways to manage this equation, but my preference is to always interact with the equation using 3 times 10 to the 8th meters per second as the value for C in this equation. So whenever I'm communicating with that equation, I want to make sure that I'm talking about wavelengths that are in meters. So that's something that we want to try to keep track of as we're doing this. Okay, so what we've got in the upper right corner here, this is the electromagnetic spectrum. So it's showing the different types of electromagnetic radiation and their wavelengths. So up top, I've got wavelengths in meters, and it's telling us all the different values. So here is long wavelength, here is short wavelength, and then down below I've got frequency, and so it's going in the opposite direction, right? Small values for frequency, oops, that's not how you spell small values of frequency on the right side, and large values of frequency on the left side. So that's kind of showing us again that things are inversely related. And then on top of that, we see the specific area where the visible region exists. And the visible region ends up going from 400 nanometers to 750 nanometers. And so in certain cases, we're going to be particularly interested in the visible region, just so we can say, is the electromagnetic radiation we're considering in this particular case, is it visible? And if it is visible, what color are we observing? So you may know the mnemonic Roy G. Biv from other applications, but that's just the colors, right? Red, orange, yellow, green, blue, violet. And so if we think about how that goes, red is in the 700 nanometer region, and violet is in the 400 nanometer region. So we'll think about that a bit more later, but we'll be able to more or less narrow down the wavelength of light we're thinking about and the color that we expect for it to see based on where it falls. So we'll take a look at that in a little bit here. Okay, so what we want to start with are just simple conversion calculations. And what I mean by that is we want to have a given frequency or wavelength, and we want to change it to the other value. Since they're inversely related and equal to this constant, the speed of light, should be pretty straightforward. Whether it's useful or not, and it may not always be useful, we're going to try to be in the habit of reporting our wavelengths in nanometers. When it's helpful, it'll help us to understand, for example, where it falls in the visible region, and then we'll be able to figure out what color it is, more or less, based on where it falls between 400 and 700-ish. Okay, so I think I said this a little bit earlier. Hertz is just the same as seconds to the -1, just more convenient to say hertz rather than seconds to the -1. Hertz is actually the name of the guy that essentially invented the radar, so that's where that name is coming from. Okay, so here's our equation, C equals lambda times nu. In this case, we want to solve for lambda, so we rearrange the equation to make it lambda equals C over nu. We plug in our values, 3 times 10 to the 8th meters per second, divided by 6 times 10 to the 4th hertz. So seconds to the -1 and hertz are the same, right? I can cancel those out. If you'd rather write seconds to the -1 instead of hertz, that's totally okay. Something just to be aware of, right? Just calculator-wise, I recommend when you start working with scientific notation values that you start putting parentheses into your calculator. All that really does is make sure the calculator knows the exponents belong with the particular value. Otherwise, it may get confused in terms of where to place it. So once we're here, where we're going to be doing a lot of scientific notation calculations, definitely use parentheses. When we do this calculation, we end up with a value in meters, right? That's the unit that doesn't cancel out. So we end up with 5,000 meters. 1 meter is 10 to the 9th nanometers, or alternatively, 1 nanometer is 10 to the -9 meters. We're going to want to be converting from meters to nanometers and vice versa fairly often. So this one's kind of the easiest one to remember, right? Nano and 9, that's the easiest way to think about it. So here where we report our answer in nanometers, all we're really doing is saying 5,000 meters times 10 to the 9th nanometers per 1 meter. Meters cancel, and I wrote 5.0 times 10 to the 12th nanometers. that's with the correct significant figures, right? Given that it's 6.0 times 10 to the fourth hertz. 5,000 is just one significant figure, so I guess I should have written 5.0 times 10 to the third, but our final answer is accurate with the correct number of significant figures. All right, so then the usual story, right? Now that we've seen one, I've got a few for you to practice on. So one is identical, right? Going from frequency to wavelength in nanometers. The other one's the opposite, going from nanometer wavelength to frequency. The units for frequency are always going to be seconds to the -1 or hertz. So per usual, pause it if you want, work these out on your own, or we'll just keep going. Okay, so top one, we're pretty much duplicating what we just did, right? C equals lambda nu, lambda equals C divided by nu. So lambda equals 3 times 10 to the 8th meters per second divided by 3.95 times 10 to the 14th. And I'm just going to write per second just so it's a clean cancellation. That'll give us our value in meters. Right, meters stays. Let's see what we get here. Three times 10 to the 8th divided by parentheses 3.95 10 to the 14th. Three significant figures here gives me 7.59 times 10 to the -7 meters. We want our answer in nanometers, whether it's informative or not. It's just a habit that we want to get into. So to do that, 7.59 times 10 to the -7 meters. Really, I'm just moving 9 places to the right, 10 to the 9th nanometers per meter. So that'll become 759 nanometers. So red, depending on your vision, ends somewhere between 700 and 750 nanometers. So this would probably just be into the infrared region, meaning we wouldn't be able to see it. Okay, next one of these, we're going in the opposite direction. So now we're going to convert from wavelength into frequency. So the given information is the wavelength in nanometers. The goal is to report it in terms of frequency. So now we have to do the exact opposite, right? We plugged in with frequency, got a value in meters, and switched it to nanometers. Remember what I was saying earlier, that whenever we're communicating with this equation, we're going to want to make sure that we have a value in meters. So now what I'm going to do is right away convert nanometers to meters, then plug it into the equation. So because I'm immediately going to use the value, I don't really need to do anything special to put the new value in scientific notation. So instead, I can just say 645 nanometers equals 645 times 10 to the -9 meters. So that's not scientific notation, right? Scientific notation, we're only supposed to have one digit to the left of the decimal, but it really doesn't matter here. I'm just pretty much immediately going to plug it in and use it in an equation. So C equals lambda nu, which now means nu equals C over lambda, C in meters per second, lambda in meters, so not 645 nanometers, but 645 times 10 to the -9 meters. So now the unit stuff is already taken care of, right? Because the answer I'm going to get out of that is in per seconds, and that's what we want it to be. So, okay, 3 times 10 to the 8th divided by parentheses 645, 10 to the -9, gives me 4.65 times 10 to the 14th hertz or per second, doesn't really matter, they're the same thing. That's the units that we end up with. So in the top one, we plugged in first, converted later. In the bottom one, we converted first and then plugged into the equation. All right, so that helps us to get kind of squared away with how to work with wavelength and frequency. I think I'm just going to make this a short video just about the wavelength frequency stuff, and then we'll do the next short video talking about the energy equation. So yeah, I'll go ahead and just stop here so you have it all in one short video.